Hey class, it's Mr. Hofstad here with our sixth and second last lesson of the year. We're looking at particle tracks and accelerators, and mostly kind of bringing some pieces together from way back to Unit 3, and then our newer stuff from Unit 6, and just combining everything into a nice cohesive package. So, particle tracks is where we're going to start, and this is essentially the paths or the tracks created by a variety of particles when they are shot through these mediums, and it's usually a liquid medium, and almost like a time-lapse photo of these, right? You get to see the particles as they're moving through, and it's like like they've almost carved out these tracks in our liquid medium. So there's an imprint of where they were, and you're able to analyze which type of particles they are just based on their tracks. Alright, so alpha particles are nice and big, right? They're our most massive particle out of these three anyways, right? They are essentially the mass of 6 protons or 5 protons combined. So it's going to be a nice and broad track, right? This thick line here is probably our best guess of alpha particle. It's got a thicker, broader line. Since they're relatively large, they're going to kind of collide and carve a larger path out of the medium. It deflects in the magnetic field according to right-hand rule 3. So remember, our thumb is the particle's direction. If we're working with positive, right, because alpha particles are positive, we're going to use a right hand. For a negative, we use left. So thumb is the direction, and then of the particle, then your finger, or all of your fingers if you're using the palm method, will be the direction of the magnetic field, and either your middle finger or your palm will be that magnetic force. So since these are so massive, they won't deflect very much, right? They have more inertia. They're going to be more resistant to that change in direction. Now, a beta particle, it's going to be thinner since it's a much smaller mass, right? These are essentially electrons or positrons, so not very massive at all. Very thin track. It's not going to displace much of the medium. So looking at this example down here, I would say those two thinner lines, number 2 and number 3, would most likely be our beta particle tracks. But it also will deflect a lot more because it has less inertia, less mass. If this is a negative beta negative particle, which is an electron, it'll obey left-hand rule since it's negative. If it's positive, it'll be right-hand rule. So again, following those rules back from Unit 3, you can go into the Unit 3 workbook if you're not remembering those right-hand rules very well, and do a quick review of that. All right, our last type that we're going to focus on today is a photon. So since they are EMR, they won't be deflected in a magnetic field. They aren't positive or negative. They don't have a charge. They actually have this oscillating magnetic field right within themselves, according to the classical theory of EMR. Since they are so tiny and so fast, they don't really collide with the liquid molecules, so they won't leave any tracks. So particle tracks of a photon are none, which is also important. But we can infer their presence because of subsequent decays. So it's not through the tracks, it's from what is being decayed, right, and what is actually being shot with these photons. So these are a little bit trickier, harder to discover, but we're getting better at it, at inferring them by subsequent decays. The particle tracks spiral, right? You see that in number 2 and number 3, since they lose energy from collisions with the medium. So if they're really light, like a beta particle, any collision with the medium, the liquid molecules in this tray or this medium that we're shooting them through, any collision will result in a tremendous loss in energy, right? They'll decrease their speed and end up spiraling as a result. All right, you can find these examples on our next video. Now, the second part of the lesson is particle accelerators. These are, you've probably heard of particle accelerators, but now we're going to kind of dig into it a little bit more, right? We've got different particle colliders, and you can do some fun digging on these more recent particle accelerators. We're just looking at one of the first. I think it might have even been the first particle accelerator. So we can only really investigate the nucleus by itself if we're able to strip it of its electrons, and that can only be happened when we shoot incident particles with a lot of energy to overcome the strong nuclear forces. Sorry, this isn't to strip it of electrons. This is actually to break apart our nucleus and to overcome the strong nuclear force between our protons and neutrons. So since that strong nuclear force is the largest known force in nature, right, we need a ton of energy to actually break it apart and overcome that strong nuclear force. So they need to be in the order of giga electron volts or tera electron volts. In nature, that can be achieved by cosmic rays coming from solar flares or supernova. Those are mostly protons that are ejected with tremendous amounts of energy from our sun or from other stars. The energies of cosmic rays can range from 10 to the 2, so that's just shy of a giga electron volt, all the way to 10 to the order of 14 mega electron volts, which we don't have a prefix for in our data sheet. That's extremely large. Most of them are absorbed by the Earth's atmosphere, so very few actually reach the Earth's surface. So you're not getting these particles actually breaking apart the strong nuclear force in nucleus on Earth very often. So we need to artificially create incident particles with enough energy. So we need to have a reliable, controllable source of high energy particles, and that's where our particle accelerators come in. So particle accelerators are essentially created to tear apart the nucleus, investigate the nucleus, do science on our particles in lieu of these high energy cosmic rays, which don't occur as often, and we can't just command them at our will like we can command these particle accelerators. So the cyclotron, created by E.O. Lawrence in 1930, has these two hollow D-shaped chambers, which they actually call these. They're filled with a magnetic field powered by this alternating current source. So that is quite a strong magnetic field, and it starting with this proton in the center here being ejected and traveling in these uniform circles across this gap here. So the D's are separated by this gap, which contains an alternating electric field for linear acceleration. So you're getting an electric field almost between two plates. It's similar to that. These aren't actually plates, but we are still accelerating our proton, right, from our positive to our negative end. So we're getting a linear acceleration when it's crossing the gap. Each time the proton goes across the gap, they're going to speed up, right? There's an acceleration. They're obviously going to increase their velocity. Each time the proton, eventually when the proton reaches the maximum speed, right, it's all the way out here at the radius, it exits the cyclotron and hits its target. So it's speeding up, and with an increase in speed, we have an increase in radius until eventually it exits the particle accelerator with its maximum speed and can hit this target atom with enough energy to overcome strong nuclear force and separate some of the protons and neutrons for our scientific reasons. So since the particles are constantly accelerating at very high rates, they're going to lose a lot of energy as high frequency EMR. That's called synchrotron radiation. So you're going to have different gamma radiation kind of lost throughout this, but you're still having enough kinetic energy within this particle to accomplish what we really need. All right, that's it. Only one more lesson. Take a look at the examples on this second attached video, and hopefully this isn't too much of a struggle, this lesson. Hopefully it's pretty straightforward. Our last one is going to be a little mind-bending, so get ready. All right, good luck.